All right, so today we are moving on from our talks on continental drift and seafloor spreading and plate tectonics, and we're moving on to talking about earthquakes today. So for a really long time, scientists have been mapping out where earthquakes occur. They just had a world map. Every time an earthquake occurred, they would put a dot in that location. And they quickly were able to start to see that these earthquakes aren't distributed equally across the world. They are in certain areas. As we learned more about plate tectonics and how the plates were moving, they were able to make the conclusion that those earthquake zones tend to be at those plate boundaries. So what is an earthquake? An earthquake is a sudden movement or vibration of the ground when the rock slips along enormous cracks in the Earth's crust. So what are those cracks? You can think of those as the fault lines, those boundaries between two plates that we talked about last week. We talked about the plates being very active, and when those rocks move, they can slip and cause this earthquake. Okay, it's the shaking of the ground that causes buildings to collapse, and it's the buildings that collapse that cause the death and the destruction. It is not the actual shaking that causes the death. Okay, if I was in the middle of a prairie and an earthquake occurred, there would be nothing to fall on me. I would survive it without a problem. Okay. So what is the cause of the earthquake? Okay, there's forces that are acting on the rocks. Okay, as those rocks are subducting or sliding past each other or pushing against each other, there's stress that starts to build up. Okay. And there are four types of stresses. The first one is a compression stress, squeezed or shortened. Okay, that's when things are tightened up together. If you've ever worn compression shorts or compression pants, you know what that squeezing feels like. Okay, it's taking your muscles and squeezing them nice and tightly together. Compression stress is when the ground is being pushed together, so it gets squeezed together and it gets shortened. Second one is a tension. This is stretched or lengthened. Okay, when you pull a piece of Laffy Taffy, okay, we're stretching it, we're lengthening it. Eventually, that stretching can snap. Okay, shear. Okay, moving in different directions along a play. When you rub your hands back and forth together to keep them warm, you can think of that as shear stress. They're moving along a plane just in different directions. And then there's torsion. This is a twisted one. This is really the most severe one because things are happening on multiple levels. Torsion stresses tend to be found deep in the earth when there are subduction zones. Okay. So when these earthquakes are sliding past each other and snap and release that stress, some deformation occurs. Okay, and there's two types of deformation. The first is elastic deformation, and this occurs when the material snaps but goes back into its original shape once that force is released. You can think of this as an elastic waistband or elastic hair tie or a rubber band even. We pull the rubber band, we apply a stress, but when we let go of that rubber band, it snaps back into its original shape. The other type is a plastic deformation. In plastic deformation, the stress happens, but the material is never the same again. Okay, way to remember plastic. If you've ever stretched a plastic bag, you know that once you stretch it, it's not going to be the same anymore. You get those waves and ripples and stuff in the bag. So that's a way to think of plastic. So elastic, think of an elastic rubber band. Plastic, think of stretching out a plastic bag. Okay. Modeling clay would be another example for plastic deformation. If I put my hand on it, it gets that stress. It keeps the shape of the stress. Okay, so these stresses build up, and eventually that energy has to be released. And it's not until the energy is released that we feel that rock move. Okay? A fault is the crack that the rock has moved on. So rocks move along fault lines. There are fault lines all throughout the world. Some just aren't moving as much. There's not as much energy building up, so there's not that strain to be released. Other fault lines are very active. Think the San Andreas fault line. Okay, we're constantly hearing about earthquakes that occur. And there's other fault lines that are even more active than that San Andreas fault line. Okay. When the strain energy is released, the rock bounces back and you get that elastic rebound that we had talked about. Okay. The elastic rebound is what produces seismic waves. So timeline here, the rocks are pushing together, they're subducting, they're pulling apart, whatever direction they are moving based on what type of plate boundary it is. Okay, that energy gets released. Okay, the rocks move, we get the seismic waves then produced from that snapback. Okay, so seismic waves, okay, travel out from the focus. So this focus here, this area underneath the ground, is where the actual snap bounce back occurred. So that's the focus. The epicenter, you'll hear it in the news, the epicenter of the earthquake was 6 miles east of downtown Los Angeles. What that means is where on the actual Earth's surface. The actual release, the focus, might be 6-7 miles into the Earth's crust. But the epicenter is what they tell us in the news so that we can have an idea of where that earthquake occurred. So make sure you know focus versus epicenter. All right, so seismic waves are sorted into 2 types of categories. Body waves are the first ones, and those are the ones that travel through the earth. And we'll talk about the 2 types, primary waves and secondary waves. So both of those are body waves. Primary waves, we will abbreviate P waves. Secondary waves, we will abbreviate S waves. And we'll talk more about those here in a few minutes. And then we have surface waves. Surface waves travel across the Earth's surface. And each of these types of waves travels very differently. So we're going to talk about the motion, we're going to talk about their speed and everything. Please make sure you remember primary waves are P waves, secondary waves are S waves. Surface waves we do not abbreviate, so make sure you write surface waves. If I see an S wave on a lab, a study guide, something like that, I'm going to go with that you are talking about secondary waves. So some more on these primary waves. Again, like a P wave. Travel along like a coiled spring. So if I had a slinky and I laid it out flat on the floor and I pushed one in, I would see how that push traveled along the entire slinky. That's a P wave, also called a compression wave. Okay, it moves back and forth. Okay, it can travel through both solids and liquids. Okay, as that wave goes through, there's not going to be much change to the surface through the earth because everything just moves back into its original position. Okay, so primary waves are not causing damage. Primary waves are very, very fast waves. They are primary. It's the first wave that will hit any place on the Earth's surface. Okay, again, very important that you know that they go through both solids and liquids. Okay, the speed, 5 to 7 kilometers per second. Okay, these are the fastest of the seismic waves. Secondary wave, again, S wave. Okay, these travel along like a moving rope. If I had a rope and I tied it to a pole and I shake the rope, that rope is going to have kind of that snake-like S wave, S shape. So you can think of S waves like a moving rope. Okay, they cause some perpendicular movement, so that up-down direction. But again, things return back to where they are, and life is okay. These aren't, again, what causes the damage. Okay, S waves, though, can only move in solids. So if they hit liquids, they are going to stop. They don't have the right movement to travel through a liquid. Okay, they move slower than P waves. Okay, they're secondary waves. They are the second waves that will hit any seismic station that is measuring and recording earthquake waves. Okay. Again, here is an example now of P waves and S waves. Here you can think of this as the slinky. One person's on this side, one person's on this way, and you've got the floor and the slinky. And someone on this wave just pushes the slinky, and you get those compression things. Here for the S wave, imagine this end is tied to a pole or something, and I'm on this end shaking the rope. Final type of wave is a surface wave, and these are much more complex when it comes to their movement. They are more of a rolling motion like surface waves, so they're moving up and down, but they're also moving in a circular pattern. Okay? They are what cause the damage to structures. Okay, it's the surface waves that cause the damage, not the primary, not the secondary, but the surface waves. Okay. In your textbook, there should be visual clips of P waves, S waves, and surface waves so you can see the difference in the way the three move. Okay. Many times in the news we hear about an earthquake measuring 5.3 on the Richter scale, or 6.2, or 3.5. But what does that mean? Okay, there's really two scales to measure. The first is the modified Mercalli, and this one we don't hear about in the news. Okay. The second one is the Richter magnitude scale. This is the one that we hear in the news, and we'll talk about why here in a second. Okay, the modified Mercalli measures damage. Okay, and it ranks earthquakes based on the amount of damage that is caused. It ranks it on a scale of 1 to 12. We'll show you that here in a second. So here is the modified Mercalli scale. As you see the intensity, as you go up from 1 to 12, the observed effects are very different. However, with the modified Mercalli, you can think of this somewhat as a social factor scale. An earthquake that hits a third world developing country, think Haiti a few years ago, a much smaller earthquake is going to damage a lot more structures than that same earthquake hitting in downtown LA, where the buildings have codes that they are built to withstand those earthquakes. So it's not really comparing apples and oranges, because yeah, you can see what happened, and the sociologists and Red Cross would be very interested in this for how much damage is there, what kind of death and destruction, but it doesn't tell us as scientists much about the earthquake. The other one is the Richter scale. And the Richter scale is much more scientific. It measures the amount of energy released during the earthquake. So a 6.0 earthquake in Haiti and a 6.0 earthquake in Los Angeles are going to be releasing the same amount of energy. Okay, what happens is those seismic waves are released from that focus, and seismograph stations record the vibrations, and then through those vibrations, depending on how strong they are, is how we can develop and see and rate what that earthquake is on the Richter scale. Here's what the Richter scale looks like. Okay, as you go up from 1 to 10, you are multiplying by a factor of 10. Okay, that's what the word magnitude means. We're in an exponential graph here. So a 6.0 is going to be much more intense than a 5.0. The difference between a 1.0 on the Richter magnitude scale to 2.0, that difference is going to be completely different than the difference between a 6 to a 7. Okay, 6 to 7, you're going to be talking major. As you get up to 7, 8, 9, you are talking some pretty strong earthquakes. Okay, so please know that a 2.0, okay, those happen all over the place all the time. But when we're talking an 8 and 9, you're not getting very many a year. The number here in the middle is about how many earthquakes per year happen throughout the entire world. Okay? There's earthquakes happening all the time. We just don't hear about them until we get really into this 6 area. Sometimes you hear about 5s if they're nearby or if they're in a very poverty-stricken area because of the damage they occur. But usually 6 and 7s and 8s are the ones that we hear about in the news. Okay, again, the damage can vary greatly. That modified Mercalli scale shows us that the same intensity of an earthquake can cause very different damage. Okay, the Haiti versus the Los Angeles. However, we cannot build buildings yet that are completely earthquake proof. We can build earthquake resistant, and out in California, right along the fault line there, they have codes that the buildings have to be so earthquake resistant. They're meant to sway. Okay, if you've ever been in the Arch in St. Louis, on a windy day, you have felt that sway. It has to. If we built that structure very rigid, okay, as soon as a strong wind, the arch would break, it would crumble, and it wouldn't be any good. So it has to have that sway. Skyscrapers are built that same way.